Okay, good morning. So today we're going to continue. This is the second to the last lecture for our just before the long test.
So did you make me present?
Yeah, I will mark your attendance later. Okay. So you didn't say the password, Mr. Temana. We know we have a password. Okay, can you say the password now while it's being recording?
The internet was giving me a hard time.
Okay. Okay. Now let's.
Really say
Okay. Yeah. So let's continue. So we will take care of attendance after the class. Okay. So now let me share the screen. So as I mentioned, this will be the second to the last lecture. So the next week I'll finish. Today going to finish a support vector machine, and next week I'm going to finish a neural network. Okay, and then December 10 will be your long test two. Okay, so I already posted the second. By the way, there's a problem with Blackboard, so I extended the deadline for submission for lab number 6, and that one will be. If you pass it, submitted it through hard copy, that's fine. If you still want to submit it through online, through Turnitin, you can also submit it because I extended it because of the technical problem. So that will be next week, the same deadline as the support vector machine deadline. Okay. So the support vector machine will go back to the Turnitin submission because Blackboard is already working. So the our TA, Ms. Osejo, can mark them nicely. Okay, so now let's. Last time we discussed about a support vector machine, and we say that there's one method of optimizing it. So it is not just about looking at the separation of the two classification. For example, classifying like this, as long as everything is well classified based on the data that is used for training. But sometimes it can be classified in this manner so that the margin between the data is larger, although it is here in this case there is one misclassification. So somehow there is a compromise, but the major objective is to maximize this margin of separation. As we know, there could be sorry, how come annotation come up now? Annotation there. So there could be possible way of separating them like this. There's another one hyperplane like that, or it could be closer and closer like this. That's also another hyperplane. But then there is less margin between the hyperplane and the support vector. Okay, the separating hyperplane and the support vector, there is less margin. So we prefer, of course, this hyperplane where your margin is large. Okay, so therefore when we try to optimize SVM, support vector machine, we're trying to maximize this. We're trying to maximize the margin by minimizing this value. Okay, so we already derived that. We know what those values are. They've been derived previously, and so we say that we maximize. Okay, we maximize the margin. How come we maximize the margin? And the norm of the or it should be minimized. We are minimizing the norm of W. I thought we are okay. The margin. Oh, sorry. The margin. The the magnitude of the margin is equal to 1 over the norm of W. And so when your W is smaller, the margin becomes bigger. Okay. So that's why the objective function is to maximize this, which is this one is the margin. So that is the margin. And then now, of course, if you want to invert it, so you're going to, instead of maximizing the margin, that means that we are going to minimize the norm of W subject to these conditions. Okay, so we mentioned that to maximize that, there is the objective function minimizing. to maximize the margin, we try to minimize the norm of W plus some value C, okay, subject to these conditions. And so the C is the regularization parameter, and there are many ways of solving that in such a way that we say we don't go through the details, but now what there are two parameters that we are going to minimize. So we want to minimize this regularization function, which is the norm of W squared, plus the loss function, which is this function. Okay. So how do we try to do this? So now in this case here, it becomes an unconstrained optimization. Okay. No more constraint. That means as long as we try to minimize W plus the norm of W plus the loss function. And so we say that to maximize, I mean, to achieve that, to achieve this objective function, we are going to, well, this part here of the loss function is, we call it Hinge loss. So there are ways to express it. And we say that it's a convex optimization. We just skip that. And so what we uh, uh, discussed last time was that finally we get a minimization, which is of uh, this expression that is based on all the data points in the classification. Okay, that means that the classification, the sign yi is the sign of the classification. Okay, and then xi is the computation of the data based on the weights plus the offset. So you multiply that, and then you go through all the data points. Okay, and so now we can combine them together so that for all the data points, you're going to minimize the normal W as well as this, whichever is maximum, whether zero or the difference. So that means that we don't go negative sign. So now we take the Lagrange of this function and we try to minimize it we take the derivative with respect to W. Okay, and then this is the function, and for this part, which is the hinge part, and then this part, which is the bottom part. And so the optimization here is zero. And so now we come out with the final way to optimize our weights. So based on this function that we want to optimize, and so we are going to update our weights. So to update our weight, again, we can think of it as equivalent to a gradient descent method, where your weights is updated based on the gradient of this function that you're going to minimize. Okay, so that means that this function that we're going to minimize, you take the gradient with respect to the weight. Okay, with respect to the change of the weight. And so now we just substitute this whole function here in this form, and we take the gradient with respect to the weight. Okay, so now this part is so if you take the derivative, there are two parts. Yeah, so if this part, we say already that this part can be because this is not continuous, can be separated. This part here, the gradient of L with respect to W, and this part, the gradient of L with respect to W. So we take the gradient of the this part with respect to W, which could be this or zero. Okay, so now if you go back here, so we take, okay, okay. So now if we take the gradient of this second part, yeah, so we have this part which is already computed for us, and the other part is zero. So we get this part when yi and f of xi is equal to zero. That means that for all the data set, you're going to compute the ith point, the sign of the ith point, times the f of xi, which is weight times the xi plus the offset. Okay, so this is the value and multiplied by the current weight. Okay, so the question is, how did we get the gradient here? So we take the gradient. So we take the gradient there. Okay, so if you take the gradient of this, what will happen? You take the gradient of this form. and then you take gradient of that form. Okay, so that means we take the gradient with respect to WT. Okay, so now this part is that part. You take the gradient of you take the gradient of L with respect to W, which in our case, we computed already here, take of L with respect to W, with respect to W. And so it will be, if this is the case, you take the Y, this is independent of W, and then this is dependent of W, okay? You take the gradient of W here, and so this one becomes 1, and you're left with Xi. So now this is this part, and so here, of course, the other side is only L when it is becomes 0, so that's 0. So this is taken care of. Gradient of L with respect to W is xi and a 0 here. Okay. What about this part? What happens here? Why it becomes just like that from here? Anyone? Mr. Tom.
Well, the two cancels two. So.
Yeah, the two cancels. So lambda over 2. So what is the equivalent of the norm? What's the expression for the norm? What's the expression for the norm? What's the norm of W? How do you take the norm of a vector? Okay, if you take the derivative, what happens here? So take the derivative with respect to W, what happens? So the 2 cancels 2 like that over 2, okay, times the norm of W times the gradient of this with respect to W, that's 1. Okay, so that cancels, and so this one, and then what is this? Is this the same as WT? Hmm? What is the norm of W? Is that equal to the norm now? Okay, the norm of a vector. What's the norm of vector V? What's the magnitude? Square root of V1 squared plus V2 squared plus V3 squared plus and so on plus Vn squared. Okay, what is that? Okay, that is equivalent to V transpose times V. Why? Why? What is V transpose? V1, V2, and up to Vn times V1, V2, up to Vn. Okay? So you multiply that V1 times V1 squared plus V2. Okay? So this is equivalent. Okay, now this is true. This is the norm of W. And so now what happens? You take the derivative. What is W times W squared? Is it equivalent to W squared square root? Looks like, okay, when you take the derivative, what happens? Well, there's a squared here, square root times a squared, so that one goes away. So what happens? This one cancels with this, okay? And then this W transpose of times W. What is that? Okay, okay. So, okay, anyway, let's just make it simple. Let's not go to the details, but anyway. So this is equivalent to this one cancels out, and now this is W that is squared, is equivalent to W squared somehow. Okay, and then this is lambda times times lambda divided by 2. And so when you take the derivative of that, so it will be what? So the 2 will cancel, and so we're going to have, if you take the derivative of this with respect to W, okay, okay, I'm just taking the shortcut now, okay, so that we don't spend a lot of time. So now it will be 2 over 2 over 2 times lambda times W and derivative of that W with respect to W. Okay, and this one is 1. And so now this one cancels, and so you're left with lambda of WT. Okay, anyway, I'm just trying to show you that this is based on the gradient of this cost function that we're going to minimize. And the cost function is a function of the norm of W, which we're going to minimize, plus this gradient. This Lagrangian function, which is the loss function. Okay, so now what is well, we're done. Yeah, we're done. This is based on the gradient descent method, and so we can choose the weights that we want. Okay, and then why do we need to, why why we don't stop here? Why still we need to continue to look for the W, so that we can we can look for the hyperplane and maximize the margin, which is a function of 2 divided by norm of W. Why? This is our margin, and this is already maximized. Okay, our margin is already maximized once we compute this. because we are computing it based on the gradient descent method. What is not good about this? Okay. Well, I will tell you. What is not good about this is it's based on I. What is I? I is the data point. Okay. So that means that you have to correct your weights as you go through all the different I's. Okay. If you have 1,000 I's, you're going to correct this with respect to those 1,000 I's. Okay. So it will become a very tedious process. Okay. Well, if you go through 1,000 I's, this one is not about summation of with respect to 1 divided by n. There's no, because this one went away. There should be a summation of 1 divided by n. Okay. So anyway, uh, so that means that, for example, if this is, so you're going to add it to all i's. So if, because they combine this one to all i's, you sum this one through all i's and sum this one through all i's. So that means that you have all this with respect to w. And so the w with respect, there should be a summation. Okay. Okay. So let's just take what is given to us now, and this is about the summation is gone. Okay. So let's take. I have to investigate this. I don't want to, because for sure there's a reason for this, and I don't want to change what is. I adapted this equations, and I will investigate, see if there's a summation somewhere. But for now, okay, what I see from this expression is that we are going to step through all the i's to update the weights, okay? But if there's, for example, if there's a summation here somewhere, okay, then you have to sum to all the weights. Okay, so that means that the weight, this weight, is summed through all these points, and so it's a lot easier. And then based on that weight minus this value, then you can compute a single update. Okay, but if there is no summation, then you have to update through all every data point you're going to update, and that will shift the weight function, many is like almost randomly. But anyway, I think there should be a summation sign here. Okay, but I don't want to do that because I'm adapting it, and so I have to investigate where really if there's a summation or not. Okay, but I have seen this expression without summation many times. But anyway, I believe there should be a summation. Okay, so now let's do that for now. Let's accept what it is there. Uh, I'm going to tell you, confirm it in the next class, whether there's a summation or not. But for now, there's no summation. And so what this part is tedious because your I will become, you have to update the weights based on all the data I, 1,000, for example, or 10,000. That's very tedious. So now, okay, but it is good because this one you can verify whether your weights is indeed optimized based on all the data sets. Okay, but let's keep this for now. For example, in our test, we are going to compute the other method that will be presented later, and then we're going to use this in order to confirm your weights. Okay, please note that one down. It will come out in the test. Okay, but I will confirm if there's a summation, no summation or not. Please remind me next meeting. Okay, now let's proceed. Okay, so we are finished with one approach where we optimize our weights based on this computation. Okay, where we have to go through all the I data points. Okay, now we consider the primal and dual SVM. uh, the way the dual is stated is that there is an alpha yi xi. So if you can see uh, here, maybe this is a lot better. So in the primal expression, our fx is expressed as wtx plus b. Okay, this one we know. We have seen that one many times in the figure here. Okay, this is f of x wx t plus b. Okay, so now there was at one point there was this one, a dual that was expressed that I didn't emphasize. But now here we are saying that those two expressions are equivalent. Okay, they're called, this is the primal wxt plus b, and the dual is alpha. There's an alpha factor times yi and xi times t. So how is this computed? How is that computed? How is this expression arrived? Is there a similarity to one versus the other? Is there something that was modified? Okay, well, there's an x here. There's an x here. Okay, here wt is expressed, replaced with this. Okay, is that correct? Well, yes. Okay, this is another way of expressing W, which is based on optimization equation. Okay, I just want you to see what is going on here, where W is expressed as a summation with this one. We can see that in the later on in the expressions, W is xi times xi. Okay, which is exactly that part. Okay, and then multiplied by the x. Okay, so anyway, so that is what is replaced, this whole thing multiplied by the x plus the b. Okay, so that is how the dual is being expressed. So why, where is this expression? So let's here, it is derived from here where you expressed the Lagrangian of the primal. And so if you try to get the minimum, okay, let's just go through this one and say that there are two parts here. This part is the Lagrangian, and then the other part you have some new constraint that is being computed. Okay, so if you consider this part only without this residual, okay, so now we can say that this part, if you try to take the gradient, okay, it will take the gradient, and if you take the gradient and equate it to zero, that means that this is the optimal uh, condition. Okay, if this is the optimal point. So in this case here, if you take the gradient of L only this part, okay, it will come out with equal to W minus this expression is equal to zero. So that means that this expression, when equal to zero, becomes the optimal weights. And just you transfer to the right side. Okay, we don't need to go through the details. I just want you to show it to you that this whole expression is in a Lagrangian form, or an equation. Let's just say it's an equation, that the gradient is an equation form, so that only this first part, if you try to optimize it, it will result into a W in this form. And so the W, therefore, this is what I showed you. The W can be expressed. The W that is the optimal W, okay, can be expressed in this form. So that is the result. So don't mind about the rest of them here. So here, that is the result of where your W is changed, okay? Is substituted by this expression that becomes the dual. So the two things are equivalent, okay? So now what you have is you have an alpha, okay, which was not here, of course, and here we don't have the weights, but you have the xi, which is the x of the data point, yi is the sign, and some value alpha I. Okay, so that's how the expression of the dual is. Okay, anyway, so now just remember this expression because it will be used several times later in our computation. Okay, so and the other part is that so in the dual, we are going to consider two things. One is the alpha I, which is some value that we're going to compute. And then this alpha I is used in this expression as well as the kernel trick. The kernel trick is just a dot product of your x, that is the data point, or of your x that is somewhere in the in the feature space. Okay, but let's continue because right now there's so many information that I'm trying to throw to you. It may be too much for your understanding, but we are going to solve it using some examples for you to be able to understand. Okay, now there are two parts that I want you to consider. One is an example of an SVM that is trivial. That means it's a linear SVM, linear in the input space. Okay, linear, you don't need to transform into another space to separate them. And then the other one is an SVM that is non-trivial. That means that you're going to transform the input space into a feature space in order to classify them. So the idea, therefore, of SVM is to really classify them linearly. Okay, so now here, if you are given a data set like this, okay, then we can see that the separating hyperplane is somewhere here, okay? And then these are the support vectors. The support vectors are, of course, we know that support vectors are the vectors that are closest to the hyperplane, okay? So for the negative values, or what is this, positive? Is this positive? It's not stated here. Is this a positive? Okay, later we'll see. The blue is a negative classification, okay? So the blue is a negative classification. It's not stated here. Blue is negative, and then the red is positive classification. So these are the support vectors that are very, very close to each other. I mean, very close support vectors that are close to the hyperplane. Okay, for the negative classification, and then for the positive classification, this is the hyperplane that is closest. I mean, this is the vector that is closest to the hyperplane, and so these are the support vectors. So the one thing that we have to understand now is that we don't deal with the rest of the data now. Okay. The way I'm presenting now is a solution that is different from the one that we computed using gradient descent method. Now we are going to use that information of the weights that is based on the expression of the alphas, where you're going to find optimal weights based on the alpha computation. So now we say that this so we are given three support vectors. We are going to compute support vectors only, not the rest of the other data points. Okay. So now try to consider that in this approach now, I'm going to consider only those vectors that are very close to the hyperplane. Okay. So normally it is given to you. These are the support vectors. Okay. If these are the support vectors, then you have to compute the hyperplane. Okay. Okay, so now, so we enumerate the support vectors. So this is support vector 1, and this is 2, 1. So this is 2 and 1. That's correct. Support vector 2, that's 2 and negative 1, 2 and negative 1. And support vector 3, that's 4 and 0. Okay, and so we augment by a bias 1. That means that we want to include a 1 here that is offset. Then later for us to compute for the B. Okay, so that in the computation, B will be included. So now, we use this as our modified support vectors. Okay, so my point is that before I proceed, we already know this expression that the optimal weights I computed using this xi, the points in the data set, and the yi is their sign, and the alpha I is just some value that we need to know. Okay, so now So we consider only the support vectors. So these are all the data sets. If we consider only the support vectors, so this is alpha I times Si is equal to W. Okay. So now, if you, that is only for the support vectors. Okay. So now, if you multiply the same sides as the support vector Sj, for example, so Si are given to you. So if you pick one support vector and multiply it with a W, it will result into a plus or a minus one based on what is the sign of the Sj of the support vector. Do you agree? Okay. Is equal to now alpha I Si dot with Sj. So now we are left with this expression. Do you agree that this one will come out with either the positive or negative sign based on what is this Sj? Okay, maybe it's not very clear to you, but Sj is a support vector, which is also just an X, yeah? It is an X. Because remember here, okay, these are data points, yeah? We just call them support vectors because they are close to the hyperplane, but they are X. It's a data point. So if you have an X, if that is the X, so that means that W times T times your X is equal to what? Okay. In this case, this is an augmented form. So that means that it considers X and the one here, and there's a B inside here. And so that means that it becomes a W transpose X plus B. And so what is this now? It depends on what your X is. Is this plus or minus one? Okay. So now, because the examples discuss this, I want you to know where these equations are coming from. So this is based on this expression that the weights can be computed by the summation of alpha I times Si based on this expression that was computed before for optimizing the Lagrangian function. Okay. So now let's continue. So the same thing, we are given the support vectors, and so using that equation of this equation, depending on what sign Sj is, and so you have alpha I times Si times Sj. Sj, remember here, J does not change, so only Si changes, the summation of all the Si's, and so therefore, so here alpha 1 S1 times this is Sj1, okay, times this one is changing. Alpha 2 S2 times this one remains the same. Alpha 3 S3, okay, because this is the summation. Remember, this is a summation that's changing according to the number of support vectors multiplied by that particular support vector. And our support vector S1 is a negative class. And so that's why here, you see, this is based on what is the class of the S1, okay, on the support vector. So here, so just remember this is changing, the index is changing, and the S1 remains the same, and then the class is the class of S1. So we'll just repeat, this is changing, and S2 remains constant, and the class is -1, and these are changing, and the class is +1. Okay? And those are the three equations that are based on the three support vectors. Okay, so we don't need to worry because the this is based on, we are already told that if we compute this equation, the weights that you will come out with this computation will be the optimal weights. Okay, so now we only consider those equations, and so now it becomes very easy on how to compute the support vector. Okay, so we, based on the augmented support vectors, so we just substitute the values. S1, S2, and S3. S1, okay, this one is all S1, then S1, S2, and S3. So S1, S1, S2, S3. The same thing, S1, S2, S3. S1, S2, S3. Okay? And then now, these are all S1s, all S1s, all S1s, all S2s, all S2s, and all S3s. Okay, there. So three equations, three unknown. If you simplify three equations, three unknown, you can compute. Okay. So in this case, alpha 1, alpha 2, and alpha 3 are computed. So now, once you know this, then we know the weights. Okay. Based on what expression? This expression. Okay. Once you know the alpha and we know the support vectors, you know the weights already. So there, then that means that we can compute the weights now based on this expression. And so we just substitute alpha 1, alpha 2, and alpha 3 were S1, S2, and S3 summation. We know all of this, and so the weights is 1, 0, and minus 3. So this is weight 1, weight 2, that corresponds to X1 and X2, and this is your B, minus 3. Okay, there. Okay, so now the computation of the weights, that the optimal weights becomes trivial. Okay, especially if your data can be am I recording or no? I think I'm recording. Yes, I'm recording. So especially if your data is what is this, if your data, if the support vectors are given, yeah, if your data is linearly separable, the input data. Okay, now it becomes very trivial, it's easy to compute. But the problem now is that what if the case is not trivial? Okay, not trivial meaning the input data cannot be separated linearly. Okay, now, for example, okay, now this is clearer. I should have this legend. Now this is clearer. So the red ones are negative and the blue ones are positive. So there's no line that you can separate these two. You cannot do that line. There's no one line that you can separate. Okay, because here the blue is here. There are two blues there. Even if you do here, there are two blues there, like that. Yeah. So therefore, the line that separates the data is somewhere like a circle. Okay, it's not a line. So that means that they are not linearly separable. Okay, so let's start first by saying the positive data, listing the positive data to be 2, 2. So where is positive is blue, yeah? 2, 2, this is positive, and 2, negative 2. So this is 2 and negative 2, that's that one. And 2 and minus 2, that's that one. And minus 2 and 2, that is that one. Okay, and here the negative data set is 1, 1, and so on. 1 minus 1, minus 1, 1, and minus 1, 1. Okay, so we're just separating the data set. Now, let's continue. Now, if this is from the input space, which we know we cannot separate linearly. So we change the space. We bring them somewhere else. Okay. So now, if we choose, in this case, we choose a certain feature. Okay, this is the tricky part of SVM. Maybe I'm thinking maybe this is the part where sometimes SVM, I mean maybe SVM, I mean neural network can become more accurate than SVM, because somehow here we need to, SVM has to come out with a particular transformation, and that transformation may not be correct. So we have to transform it into, we have to go through all the possible transformations where you go from the input space into the feature space. And what kind of transformation is that? You're going to find it yourself. Okay, so now, well, in the test maybe it's given to you, yeah, but in the actual world you don't know what it is, so you have to find it yourself. So now, and the test, and then you later test if this one is working or not. So now we say, for example, here, this is this case here, the phi1 is not, we call it the function that defines the feature. Okay, so we transform from the input space, which was this space, into another space. Okay, That where we can now separate the two into using a line. Now, if you can see, without looking at this, we can see that here, you can separate them linearly already. Okay? You understand? You find it interesting? Hmm. Mr. Buaho. Okay. Anyway, so just like space, in space, no? Sometimes, we don't know the real world. We see only the space of the dimensions, okay? The depth and all these orientations like that. But inside the person, there is also another space, yeah? Okay, a space that we don't see, or we only see it because we see the expression of being happy and sad face, for example. Okay, but deep inside we don't know if somebody uh, will be happy in the actual space of the emotion, for example. Okay, it's showing happiness, but the real score is actually, not happy. Okay, if you go into that space. Okay, so there are many ways, for example, this person, okay, is not, let's not go with a person. It's more complicated, but for example, in the robot space, yeah, maybe that is easier. In the robot space, there is a joint space and the world space. Okay, so the joint space is the number of joints where the robot has. Okay, and these joints transform into the hand in the world space. So the joints itself, for example, if you have 7 joints, then you have 7 dimensional space. That is difficult to watch. That's difficult to see compared to the world space. Maybe we call it the world space here. Okay, this is the world space that you can see, and then you transform it into the joint space. So the same thing as what is happening here. You transform it into a space where you can visualize things properly. Okay, now, okay, let's not dwell with that because I'm counting the time. I have one more hour. Yeah. Yes. Okay, we finish at 1 o'clock. Yeah. So not bad. So now, okay. So now we transform this one. I think time is low today. We transform this, or my discussion is fast. Okay, anyway. Okay. We transform this into, let me note down the summation. That's the summation I need to confirm with you. Okay. So the here you create a feature space. Okay. In the feature space, in this case here, it increases, the data increases into 2. Huh? Okay. Sorry. The data is, there are 2 options. Okay. So there are 2 options where you can choose. Is still a 2-dimensional space, but there are 2 options for you to plot into the feature space. Okay. So the output of this, okay, to better understand, is that the output of this, okay, you input x1 and x2, yeah, and then the output is one of these. It's either this or this. Okay. So for example, we are going to compute x1 squared plus x2 squared square root. Okay, greater than 2. So if x1 squared plus x2 squared square root is greater than 2, then we use this. But then if it's less than 2 or equal to 2, then we use the simple equation. Okay. For example, okay, let's concentrate on this one that didn't change, on the red. So this is 1 and 1. Okay. 1, 1, 1, 1. So in this case here, 1 squared plus 1 squared, that's 2. Square root of 2. What is square root of 2? What is square root of 2? 0.707. Okay. Okay, I think so. 0.707. Okay. Should be, is that correct? Zero point 0.7 times zero point 0.7 is what? Come on, 7 times 7. That's not correct. Zero point 0.7 times zero point 0.7 is what? 49. 0.5. I think what I'm saying is 1 over square root of 2. Yes. It should be more than 1. 1.7? Is it 1.7?
It's 1.4414.
Okay, 1.414. Okay, that's good. Yeah. So 1.414. So that is the square root of 2. So 1.414 is not greater than 2. Yeah. So that means that here it doesn't change. Okay. So we are less than 2. So all of these will remain the same. Okay. What about this one? 2, 2. Okay. Remember initial. So all these data points, if you plug in here, if you plug in to check, this is all 1. So everything is 1 because it will be squared. So everything is 1 here. This is 1 plus 1. That's 2. Square root of 2. That's 1.77. So that is less than 2. So all of them will remain the same. So now all of them will remain the same. Let's go here. So if this one is 2, 2. So let's start with 2, 2. What is 2, 2? So 2 squared plus 2 squared. So this one also remains, this one, everything will be positive. Okay. So 2 squared plus 2 squared, that's 4 plus 4, that's 8. Square root of 8. What is square root of 8? I think it's greater than 2. Yeah. That's greater than 2.
Yes, sir. It's 2.82.
Yes. Okay. So that means all of these data points, in all of these data points, this equation applies. Okay. So now let's continue here. So what is x1 minus x2 an absolute value? So if both of them are positive, this becomes 0. Okay. Or both of them are the same sign. Okay. In this case, that one and that one, they become 0. Okay. So here 4 minus 2, that's 2 because that's positive, positive 2, and 4 minus 2, that's positive 2. So this one is 2, 2. So it remains there. 2, 2 remains there. Okay. So next, what about this one? Okay, let's go here because this becomes 0. So now x2 and x, so this is minus 2. So this is minus 2, 4 minus minus 2, that's 6. So it becomes, okay, this one, 6. No, sorry. Yeah, this is x2. So now, what am I doing? This one, I'm doing this one. So this part here is 0. Okay, now is minus 2, that's 6. So this one is 6. And now this is minus 2 also, that was also 6. Okay, that's okay. So next, I'm doing this one now. So what happens here? This part first, x1 minus x2. So on top, what is that? 2 minus negative 2, that's 2 plus 2, that's 4. Okay, at the bottom, no, this is 4 here because that's different sign, this part. And on top, the same sign. What's going on? Okay, so this is the same, x1 minus x2. So x1 is 2 minus negative 2, that's 4. Okay, this one is 4 and that is 4. Okay, so this is 4. So now this is 4 minus x2. So that means that is 6 plus 4 is 10. Is that correct? Is this 10? Is there something in my calculation that's wrong? So x1 is 4 minus 2. That's 2 plus 1. That's 6. Is correct? Can you check my calculation? Looks like this is wrong. Okay, let's clear it. Okay. We are okay with this one and we're okay with this one. So this one, so x1, this is x1 minus x2 minus negative 2. So 4 minus negative 2, I mean 2 minus negative 2, that's 4. So that is 4, correct? Then here, this is 4 minus negative 2. That is 6, yeah? Plus 4, this is 10. It's not 6. Ah, there, it's correct, 10. This is 10. So this is wrong. This is 10. And the other one is 4 minus 2. That's 2 plus 1, that's 6. 10 and 6 there. In the graph is correct. So 10 and 6, this one. This is wrong. Okay. 41. Okay. This should be 10 and 6. That's wrong. And then, but this is correct because the negative data, they didn't change. And so now it will be, just exchange this one. So minus 2 and 2. So again, this is minus 2, minus 2. Again, this is 4 because that's absolute value. And this is also 4, absolute value. And then 4 minus 2. Okay, that's 2 plus 4, that's 6. And 4 minus negative 2, that's 4 minus negative 2, that's 4 plus 2, that is 6. Okay, so this is 6 and 10. Okay, so here, this is 6 and 10. So here, this is 6 and 10. That's that one. So this one is that one, and this one is this, and this is 6, 6, and this is 2, 2. Okay, and this is 10, 6. Okay, please make the correction. Okay, so now those are in the feature space, and this is the negative. I mean, these are the values in the feature space also, but it's the same as the input space. So now we have this data, and now we can separate them. Okay, so we apply the same equations. Okay, we apply the same equations of those computing for the weights, but now using the feature space value. Okay, using these values already. We don't use this value because they are not linearly separable. This one is linearly separable, and so we use the feature space. Okay, so now we just repeat the process. Okay, where we say there are two support vectors here. Okay, that one and this one. Okay, so one is positive. This is positive is blue, and so positive is blue. So this is S1, and this is S2. Okay, so S1. Uh, uh, S2 is positive. Okay, sorry. S2 is positive, so this is S2. S2 is positive and S1 is negative. So S2 is 2, 2 and S1 is 1, 1. Okay, so that's why here S1, S1, the sign is -1, and S2, S2, the sign is +1. Okay, so there are only two vectors, only two support vectors. So we compute, and then we say that Alpha 1 is -7 and alpha 2 is 4. Okay? So now we are going to plot them. Okay? I mean, the alphas are given, and then we're going to compute for the weights now. So again, based on the support vectors, these are the expression. And so we just substitute the values of alpha and SI. And now these are the results of your weights. So the first two are the W1, W2, and this is your B value, the offset. Okay. So now you can classify them. Okay. In here when you are given the data in the input space, put them into the feature space, and there you can classify them with a positive or negative. Okay, but there's something wrong here. So now, if you give for example, okay, this is how you're going to classify through SVM. Say you're going to compute the support vector times the data, okay, that is given to you. And then now, based on how many support vectors there are, and sigma will be the classification. So sigma will be the sign of the Z. So, we have two support vectors in this case. And so there are two values. And then our X, you apply the sigma 1 for our X that was the given information. This is 4, 5. Okay. For example, we are given 4, 5. Where is 4, 5? So we are given 4, 5. Okay. We are given 4, 5, not in the feature space, but in the here, in this, we are given 4, 5 in the input space. Okay. We want to know what is that classification. No, this is still the feature space here. So somewhere here, 4 and 5, 4 and 5, we want to know what is the classification of that data. Okay. How? Well, we bring it to the feature space. Again, here you apply the sigma of the support vector. Okay, we know that our support vector is 2, 2, and 1, 1 from the input space, and then input space also of 4, 4, and 5 from the input space, and we are going to transform it into the into the feature space. Okay, so why is this 1, 1, and 2, 2? Immediately, without going through sigma 1, 1, 1. There, sigma 1, 1, 1. Yeah, so correct. So the input of 1, 1 and 2, 2, we know those are our support vectors, 1, 1 and 2, 2. Okay, and they are the same. They are the same whether feature space or in the configuration, feature space or the input space. This was our support vector, and this is our support vector. Okay, so that's the support vector that we have chosen. I'm from the feature space, and now there's also support vector for the input space. And so we compute them. This is 1, 1 in the input space, okay, and then 2, 2 in the input space, and transform them using this function phi1. Remember, phi1, this function phi1 uses this function. Okay, so we're going to compute using this. So we just transform. Okay, so whatever is the value here, 1, 1 and 2, 2, we know that in the feature space they are, it's just this and the augmentation of 1, which is for the offset B. So now we know that they don't change in the feature space. This is the input space, and when we put them into the feature space, they don't change. All we need to do is just put an augmented 1 here and 2, 2 and augment 1 here. So that's what happens because they don't change from input into the feature space. Okay, now this is the one that will change 4, 5. So now we compute what is this part. So if x1 is 4 and x2 is 5, what is that? So what is this? 16 plus 25. It must be higher than 2. Yeah? And so we apply this. Okay? So 4 minus 5. Okay? So 4 minus 5, that's negative 1. So this is 1. Okay? That's 1. Okay? So 4 minus, okay, 4 minus 5, that's minus 1, plus 1. Okay? So this is 0. And then 4 minus 4, that's 0, plus 1. And so this is 0, 1 in the feature space. And if you augment it, it's a 1. Okay? So now, if you go here, so this is 0, 1, 1, 0, 1, 1. Okay? Multiplied by our alpha, that is 7, and alpha, that's 4. Alpha 1 and alpha 2. Any questions? And so now the result of that is sigma of negative 2. That's the sign of sigma, the sign of whatever, the sign of the input here. So now this should be negative 1. Okay? So if you go through here, that means that you plot here in the input space is 4, 5 here, then we can see that there is this separation of the hyperplane. This part is positive 1, that part is positive 1, and this part is negative 1, and there is somewhere that things, the hyperplane meets here, and also there's another hyperplane here. Okay, so now we want to say, oh, is this a correct classification? Well, maybe no. Yeah, that's why this is the thing about SVM. You know, we have to choose the correct fee, the correct transformation into the feature space, okay, to have a good classification. Okay, so now let's go to another method of classifying. Well, this is the result of our first classification. Okay, it may be wrong, it may not be wrong. Okay, it may be not very efficient. Okay, it may not be able to classify certain things, but it was able, definitely it was able to classify our data. I mean, given the data that was used for training, it's able to classify it successfully. But given new data, maybe no. Okay, so let's try another fee. Huh? Is it interesting? I think it's very interesting. Okay, so now we apply a kernel tree. Okay, so next, are you still alive? Okay, I wonder why this one didn't stop for some reason. We keep on continuing. Maybe they know that we are frequent customers. Okay. Anyway, so let's try another transformation, a feature transformation function. Okay. So in the present in the previous present transformation, we use phi1, which preserve the dimension, excuse me, into a two-dimensional case. Okay. Now let's try another function, phi2, where in this case, we want to increase the dimension from 2 to 1. Okay. So now in this case, we use the first two functions, I mean the first two values of the vector to be the original vector value. And then the third value will be this. Okay. How did we get this? Well, they get it by making sure or matching so that if your data is positive, okay, this result to be positive, and if your data is negative, it results into a negative. Musa? Musa. Okay. So now let's try another function phi2. Okay. So now if this is the transformation, okay, if this is the feature space, now we know that inside here, if you use this transformation, we know that inside here will be negative. So this is now the separation plane. There's no more other separation plane except that one. Okay. Now inside here are all negative and outside are all positive. Okay. So let's continue. So we use this new function theta 2. So now in our previous case, I'm putting here the positive data. Okay. Okay. This one is again 10 and 6, I think. And this is 6 and 10. Okay, I think that's correct. So anyway, so this is not correct. So now we change the data so that now x1 and x2 are mm, are transformed into the second function. So now the original data set is the original input set is 2, 2, 2 and minus 2, minus 2, minus 2, minus 2 and 2. So we just keep them and then compute this one. So we compute x1 and x2. So in this case, 2 squared plus 2 squared, that's 4, 8 minus 5, that's 3 divided by 3, that's 1. Okay, so here it's always 4. Okay, because here, I mean, it's always 8. 2 squared plus 2 squared, that's 8. So it's always 8, no matter what is the sign. 8 minus 5, that's 3. And so all of these are all 1. So the bottom here are all 1. And now let's go to the negative data. So the negative data are all, again, this is from the input space. Okay. Just want to, this is that input space that I'm talking about. And so your original data is all 2 and minus 2. Okay, I'm sorry, 2 and minus 2, the positive ones. And then the negative ones are the one inside. Okay, so these are all ones, just changing the signs. And the other positive data are all twos, just changing the signs. So let's go back here. So now, so you have all the positive data are all twos, changing the sign, and always 1 here at the bottom. And then the negative ones are all ones, changing the sign, and negative 1 at the bottom because of this computation. Okay, we add that. Okay, now, then we say that for the support vector, in this case, everyone is a support vector. Okay, why? Well, you can see here, this is the hyperplane, and the data set or data are close to the hyperplane. Okay, there's no other data that is closer to the hyperplane than them. Okay, and they're equally spaced. Okay, so all of them are support vectors. So now you have 8 support vectors. Okay, now you're in our equation, we need to consider 8 of those. So now we're going to consider 8 of those. So we are going to have an 8 by 8 matrix. Okay, so alpha 1, the same thing, alpha 1, and then this new, remember, it is about alpha times the feature space of S1 times the feature space of the first vector, the first support vector, then plus the next support vector, again, the same support vector, and so on. So this one can be S1, okay, S1, S1, S2, S1, S3, S1, S4, S1, like S5, S1, like that. And then repeat S1, S2, 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 S3, S2, S4, S2, and so on. Until this is all about S1 to S4 are all the positive classification. Okay, so you have 4 equations with positive classification from S1 to S4. Okay, then you have another 4 equations. We have negative classification from S5 to S8. But then you have to multiply it from all the support vectors S1 up to S8. Okay, so that means that you will have 4 of these equations, another 4 of these equations. And you plug in the information, it will be like this. Okay, an 8 by 8 matrix, but it is not invertible. That means that if you compute alpha, So the coefficients are the A matrix times the alpha matrix is equal to B. The B is this one, the output. Then you compute your alpha is equal to A inverse times the B. This A is not invertible. Okay, so we use, okay, I diverse from the solution of this author. Okay, I think this is the best way possible to compute. Anyway, so we have the same results of saying that the weights are 0, 0, but this one is not the same as the author. So that's why some of them I'm trying to modify. So now, because this is not invertible, and so here, if you take two support vectors at a time, so that means that I'm going to take this as one support vector and this as another support vector. Okay, and then compute using two support vectors only using our method, then I'm going to have the same alphas. If I use this and this again, I'm going to have to compute the alphas and this and that, to compute the alphas and this, I compute the alphas. So what happened is that if I take them two by two, then I will have consistently the same alphas. So the alpha for the positive side is 1/3 and the alpha for the negative side is minus 2/3. Okay, and then that means that I have 8 alphas now because these are the alphas: alpha 1, alpha 2, alpha 3, and alpha 4. Okay, they are the same value. Okay, that is 1/3. And alpha 5, alpha 6, alpha 7, and alpha 8, same value, that is minus 2/3. Okay, so that means if you add that based on the support vectors, so you have 8 support vectors that we defined already. All those vectors here, 1 2 1 2 3 4 5 6 7 8, those are 8 support vectors that's we defined as these values, 8 support vectors multiplied by the alpha, multiplied by the alpha value, it will result into 0 0 and 4. So what does it mean? Okay, so that means that what happens here when you classify, of course your f of x is equal to w transpose, if this is augmented W already, W transpose times the X, whatever your X is, plus augmented by 1. Okay? So it will result into a positive or a negative classification. But then, if this is 0 0, so that means 0 0 and 4, and this is x1, x2, and some new value that you added, a function of x1 and x2, the third value, what happens? It means that x1 and x2 doesn't matter to classify. It is the last part that does matter. Okay? So that means that whatever is the value of your x3, whenever you compute, whatever the value of your x3, this one determines the classification positive or negative. And so here, that x3 determines positive or negative. The weights in the feature space does not matter. Because, I mean, the x1 and x2 in the feature space does not matter to classify the x to be positive or negative. It is the third element that makes it positive or negative. And so now to decide whether it's positive or negative, you just compute for the x3. Okay? So that's how you classify. So from the input space, you bring them into the feature space and classify them there linearly. Okay, so whenever you're given an input space, bring it to the feature space to say this is positive or negative. You don't look at it in the input space to say it's positive or negative. Of course, you can map it back, but then when you map it back, you can already label in the input space at this point is already positive or negative. Okay, any questions? That's the end of my presentation for the support vectors. Any questions for support vectors? So again, I want to emphasize that there are three ways that I've shown you. Okay, one on how we are going to classify SVM. Okay, one is by this, which is by this gradient descent method, which I have to inform you about the summation. Okay, I will note it down. That's the first instance, but the problem here is you have to go through all the data points, and if the data points is 1,000 and you have to compute them, is a very tedious computation. Yeah, and so now the two other methods are we only use the support vectors. Okay, support vectors meaning those vectors that are closest to the hyperplane. So what are those? So now we have two exercises. One is that linearly separable in the input space, okay, where we don't need to transform into the feature space. So here we use them as it is, and then we have equations to say these equations are used for classification. And so we just apply the equations and then solve for the alphas. Okay. Then when you solve for the alphas are there, then you can solve for your weights using the support vectors, and then your weights are there. Okay. So to classify, then of course, to classify using the weights multiplied by the X input, then you can know now given this, for example, let's just take an example here. So this is your weights, 1, 0, and -3. So if I classify, okay, so 1, 0, and -3. Okay, then if I classify one point, which is, for example, this point, that is 1 and 1. So 1 and 1, and of course, augmentation 1. Okay, what is that? So 1 plus 0 minus 3. It's a -3. It's a negative classification. Is it negative? This is negative, right? Okay. We already mentioned that this one is negative and this is positive. Here is negative and here is positive. Okay. So for example, I want to use 6. So based on the weights that was given, that we computed, because we know those weights are already optimal weights. And so we can say this is 6, 0, and 1 because that is augmented. Okay. So that means 6 plus 0 minus 3. That is 3. So that's positive. Okay. So this positive belongs to positive. Yeah. Okay. So that one is already clear. So next we go to the case where we cannot have a linear separation. Yeah. We cannot, but like hyperplane is nonlinear. Okay. So now how do we do that? We transform into another space. Okay. It's critical on how you define your transformation. So one is this method that we already tested, and the other method that means that it was good in classification because now we classify them linearly, but then eventually we find it difficult because somehow the new point that we test somehow will have this kind of classification with a singularity. That means they meet in a certain point, so maybe not a good one. So now we try another transformation, which is x2 in this form that we increase the dimension. Now x2 brings into a feature space of 3 dimensions, and so in the input space it will look like now your hyperplane is this one. Okay, where everything here is positive, outside of that circle is positive, inside that circle is negative. So it looks like that's a nice classification. And so we try to solve it. And so now we're saying that based on our solution, an 8 by 8 matrix, which is not invertible, we take the solution to support vectors 2 at a time. And now we use that solution for alphas, okay, for alpha positive and alpha negative, and use the 8 support vectors. Our weight is 0, 0, and 4. So that means that in our case here, it is the x3 or the third element of our of this feature space function, whatever the third element is the one that determines the classification. Okay? So whatever is your input, you will you will use it. For example, here, let's test it. So we say that it classifies this one according to what is the value here. So for example, we take 11 and 11. So 11 and 11, what is that? 11 squared plus 11 squared minus 5. So there's a big number minus 5 divided by, I think that's positive. Yeah, it cannot be negative, right? So if you take 6, 6, so 36 plus 36, that's a very big number minus 5, that's positive. Okay, so that means that here it will become negative if this value is less than what? 5, right? Because this is minus 5. Okay, so if this is 4, what is 4? 2 and 2. So 2 squared plus 2 squared minus 5. So that's 1. Okay, 4 minus 5, that's 1. Minus 1, minus 1/3. So that's negative. Okay, so that means that inside the circle is negative. So it doesn't matter. We don't put it here. Only this part. Okay, is that understood? Okay, that's interesting. Support vector machine. Okay, so the thing is, we can classify them. Our idea is to classify them into the input space. I mean, from input space into the feature space where we can separate the data linearly. Okay, so I will use the time with the remote. There's still 10 minutes. I will use the time to discuss the undying problem of the Monty Hall problem. Okay, this time I really come prepared. Okay, I didn't stop until I can just write down my own solution. Okay, so the problem that we had was that, okay, so I'm just writing down the Bayes rule, where there are three instances, or there are three events of the car. So you have, okay, I didn't write it down, but car A, car B, and car C. Okay, is this the event where car is in door A? Whose sound is that? Who is that? Onili. Okay, let's go back because I want you to really appreciate that it is worthwhile to understand this. Okay, not just using their numbers, but we should know exactly what's going on. Okay, so car,
Okay.
you understand? Okay, who's that?
Yes, yes.
Some guy is still talking. Okay, so now, so car A, car B, and car C are the event that the car is in door A, and car event is the car is in door B, and the event that the car is in door C. Okay, and A, B, and C are the events where the host opens door B, door A, B, and or C. Okay, so now the way to interpret it is, for example, here, okay, you open door B and the car is in car A. Okay, that is what our interpretation before. Okay, that is correct. You open door B. What is the probability that door B is open and then the car is in the car A? Okay, but if the car is okay, and then we go to the other probability of a car B is when the door B is open and the car is in car C. Okay, but if now the tricky part is we have to make a choice. If you don't make any choices, these things won't change. Okay, these things will have the same probability. This part that one that we have computed. If we don't make any choice, B is open and car A, that the probability the car is in car A, I mean the car is in door A, compared to door B is open, the probability that the car is in car C, A in door C. They will have the same probability because we don't make any choice. That's the difference. So if we make a choice of say, I want to choose door A. Now, if we make a choice, then that makes a difference now. This is the part where this part changes. This part. Remember last time we say this was, I don't know, I think this is 1/3, one half because they have equal probability. Okay. Now this is the part that changes because we make a choice. We say we make a choice door A. When we make a choice door A, what happens here now? What is this probability? This is the probability that the host opens door B and the car is in car A and we have chosen door A. That means that we will win. If we didn't make a choice, there's nothing. We won't win. But now the difference is that we have chosen. We have chosen. The host opens door B, the car is in door A, and we have chosen door A. So we will win. Okay? That is the case that we will win. And then now, if I go to this side, what is the interpretation of this? The car is in door B, okay? And I mean, the host opens door B, the car is in door C, but we have chosen door A. We have chosen door A. So that means that now is it going somewhere already? We have chosen door A here. And also on the other side, we have chosen door A. Okay, so here, so that means that if the host opens door B and the car is in door A, we have chosen door A, we win. Okay. So in the other case, the car is in door B and I mean the host opens door B and the car is in door C, but we have chosen door A. That means we won't win. Okay? Because we have chosen door A and the car is in door C. Okay? So now, what's the point there? We want to know what is this probability. If the probability of this one is higher than the probability of this one, we choose door A, that means we will win. If this is higher probability, then we choose door A. We don't need to switch. Yeah? Because we have chosen door A and it's a high probability. But if you have chosen door A and then this was higher probability, we have to switch. Now because this one has higher probability of becoming the event. Now it's clear now, I think. It is clear, isn't it? Okay, now, okay. Are you convinced? I mean the beauty of how the problem was solved. Yeah. And it is exactly the same formulation, but there is something that we interpret the probabilities based on the assumption that we have chosen door A. Then these probabilities changes. Some probabilities change. Okay. So because we have chosen door A, then if this probability is higher, alone, we choose door A and the car is in door A, and then the host chose door B. If this probability is high, then we don't need to switch. Okay. But then if the door opens in door B and then the car, there's a probability the probability that the car is in door C, but we have chosen door A, okay? If this is higher compared to the previous one, then we choose this. We switch into car C, okay? What is the reason? Okay? The reason is that when we do this, actually, we are playing a trick with the host in some sense. We are playing a trick because we make a choice and the host, based on our choice, he chose something. He chose something based on our choice. And the way he chose gives us the idea that, hey, because he chose that, it gives us a hint that somehow there is that kind of choice from the host gave us a hint that, there is the probability, what can be because of his choice, where is the higher probability of the car being in a particular door? That is the interpretation of all these solutions. Okay, then let's go to the actual solution. Okay, the actual solution is that we know that the car A, this is 1/3 all the time. Okay, car A, this is 1/3. Don't look at the solution. This is 1/3 because now everyone has equal probabilities. Okay, so remember that we have chosen door A. Yeah, so now car B, car, the car is in door A, and if the car is in door A, and what is the probability that the host will choose door B? There are only two choices, B or C. Yeah, and so that is 1/2. Okay, that is 1/2 there. Okay, so car is in door B and the host opening door B, that is 0. Okay, and this is 1/3 because equal probabilities, that's 0. So now car is in the car is in door A and this was 1/2. We have solved that one already on top there. Now this is the one that makes a difference. Okay, the car is in door C. Okay, and the host opens door B, but then we have chosen door A already. He cannot. This is the one that makes a difference, us choosing door A. He cannot choose door A because we have chosen it. It's only one possibility for him to choose door B. So there's no other choice, but that's one. That is the hint that is given to us as a player by the host. Okay? And now, it's once we do this, our probability is 1/3. So that means that if we stick to our original choice, the probability of winning is less because there are only two possibilities. Remember, there are only two possibilities. It's either we choose door C, door A, or door C. So now we go to choosing door C and see what happens. Where is the higher probability? Based on maximum likelihood theorem, okay, of Bayes' rule, naive Bayes' rule, we choose all probabilities and see the higher probability is the one that will possibly happen, with more likelihood of happening. So now let's go to door. What if door C is open? I mean, what if the car is in door C? Yeah, we choose door B. I mean, the host choose door B. We choose door A, and then the car is in door C. Okay, so now this one, the same thing. Okay, let's remove everything. Now this is 1/3. Everything is 1/3. Everything is 1/3. This is 1/3, and this is 1/3. Okay, so now the car is in door C, and then the host will open door B. We have chosen door A. Remember. So what is this? The car is in door C. The car is in door C. We have chosen A. The host won't choose door C. He only chose door B. So there's only one possibility for him. That's why choosing door A gives us a hint on how the host behaves. Okay, there is only one possibility for him. It's one. He cannot choose door C because the car is there. So he can only choose door B. He cannot choose door A because we have chosen it. So door B is his choice. So there's one. Okay, so now the car is in door B again, and then this is 0. Okay, and then the car is in door C and we choose B. That is 1 because this is already, we have chosen door A. The car is in door A and the host choose door B. Okay. Well, we have chosen door A. So that means he has another choice of door is either B or C. So that means this is 1/2. Okay, now everything matches. And then this probability is higher. And so what happens? We choose, this probability is when we choose door A. Okay. But because this is higher probability now, we switch. We choose, we say we choose door C instead. Okay. If we don't, then we'll remain. If we don't change we choose car A, we choose door A here. If we don't switch, then our probability is lower. That's 1/3 compared to 2/3. So this one, we choose door A, but if we choose door A and the host behaves in a certain way, opens door B, host behaves certain way, and we know that there is the higher probability will be in the other door. Okay, it will be the car being in the other door. If we stick to the original choice, knowing the behavior of the host inside these probabilities, if we still stick, our probability of winning is lower. But if we choose a particular door and based on the behavior of the host, we get certain probability and that probability is higher, then we really need to switch. Okay? Okay, I think I'm satisfied with my explanation now. I myself is convinced, and last time, of course, I have to kill my own idea because if I'm not convinced, it's not. There's no way you will be convinced. Okay. Anyway, yeah, I, the thing is, I tend not to not to remember. I easily forget things. So okay. So any questions? I think you're ready with this one. I successfully explained to you. So the solution. And then now, because there are many solutions online, then you have to choose which one really convinces you. This one convinces me. I think this is correct. Yeah, the other solutions, I don't believe that. This one convinces me. Okay. And then I think the support vector machine, I have given you the exercise for support vector machine. Next week is the deadline. Okay. Then I'll give you the last session of neural network. Again, I will give you the exercise for neural network as a lab exercise so that you will submit. Okay. Submit it. You can submit it earlier. The neural network lab exercise, please submit it early. It's just for you to do some exercise. Okay. So that, because if I don't give a lab exercise, the lab exercise is some sort of a seat work exercise for you. Okay. So try to do that and then submit, scan and submit into the Blackboard and then get ready for the test. Okay. So that means that long test is in December. So there are 2 more meetings in the class. The second to the last meeting is a lecture on neural network. And then the next class we do the lab. The lab will be in our long test 2 that will be done in the physics lab. Okay. So see you next week for neural network. And then I will upload a neural network after the lecture. I will upload a neural network exercise, a lab exercise for you to take to do your exercise and then submit. Okay, then you will be ready. So the long test 2 will be naive Bayes rule, support vector machine, and neural network. Okay, let me ask you this question. You want to submit a lab exercise for neural network or you don't want? Answer.
We want.
Okay. I want because I also believe that you should submit. Musa! You get 3 extra points for long test. Because it gives you the exercise. If you don't submit, you don't exercise. You think that you know, but you don't really go down and sit and solve them. Okay? Okay. So, yeah. So that will be the plan.
Yes, sir.
Okay. So that's the plan. And remember, for you who didn't submit naive Bayes rule yet, I extended up to Thursday next week. Okay, so that you can have time, you can submit it online, or if not, you give it to our TA, submit it to my office so the TA can mark them using the hard copy. Okay, there's problem with Blackboard, so that one we cannot control. Okay, so I give it more time for you to submit. Any more any more concerns? If there are no more, then I hope I explained to you everything except for where is that? The summation. Yeah, I have minus summation for the SVM, support vector machine of optimization using all data points. Okay, we need that in order to for us to verify whether the results of our computation using the support vectors is correct. Okay. Okay, see you guys. Excuse me. Let me stop sharing. And now we have how many are still students? Somebody left. Okay. Anyway, I this is recorded, so I will check the attendance after recording. Okay, after the class. Okay, let me stop recording.